Well, I've come to the conclusion that providing a introduction to this audience of an overview of Major John Wesley Powell's 1869 expedition through through that 1869 expedition would provide no useful purpose. So I'll skip it and simply quote the words of one of the expedition members that they planned to map locations that had never been surely known to within 100 miles. The expedition carried with them a number of scientific instruments. There were 2 sextants. They would have looked something like this. This is an instrument for measuring the altitude above the horizon of celestial bodies, the sun, the moon, planets or stars. And from these observations, it's possible to determine latitude and longitude. Now, generally, this is a two-handed operation, and Powell, of course, had his lower part of his right arm amputated following the Battle of Shiloh, so it wouldn't have been an easy thing for him to actually operate. They also carried 4 chronometers, and the purpose of these was to show Greenwich Mean Time, which is a key component that goes into determining longitude. Unfortunately, on the 11th of July, while running the rapids in Desolation Canyon, Powell's boat was swamped, and again, in the words of one of the expedition members, that ruined $800 worth of watches. That meant that Powell now no longer had a straightforward way of determining longitude. They also carried a number of barometers. These were used for meteorological observations and also determining the heights of geographical features along the way. If you wanted to measure the height of a mountain, say, if you measure the atmospheric pressure at the top and the bottom of the mountain simultaneously, then you can determine its height. It does require that somebody carries one of those barometers up to the top of the mountain in the first place, but that's something that they did do apparently. They also carried with them a quantity of liquid mercury, both for refilling and repairing the barometers, and for use in the artificial horizon, which would have looked something like this. Basically, it's a tray with a glass roof, and there would be a pool of liquid mercury in the tray at the bottom. And we'll talk a little bit more about both of those things in a minute. Now, Powell's astronomical observations are recorded in meticulous detail in his journals, which now reside in the Smithsonian Institution. For many years, the meaning of these screeds and screeds of numbers remained mysterious. And recently, along with my collaborator Lars Bergman in Sweden, we looked at these numbers and analyzed them and have published our conclusions in the Journal of Navigation. So this is how a sextant works. Well, at sea, what you're doing is you're taking your sextant and you're looking through this. Whoops. Oh no. That's gone up. There we go. Let me put that down. So at sea, what you're doing is you're looking through this little eyepiece here, and what you see in it is an image of the sea horizon and the body that you're trying to measure the altitude of. It doesn't have to be the sun, it often is, but it could be the stars, planets, or the moon. On land, you obviously don't have a sea horizon, so in that situation, what you're doing is using this artificial horizon with a pool of mercury, and you're looking down into it, and you're measuring the angle between the body and the sky and its reflected image in the artificial horizon. Now, just because of the geometry of mirrors, the angle between those two things in the artificial horizon is twice the altitude of the body above the horizon. And a sextant can measure angles up to 120 degrees. That means that the body you're trying to measure the altitude of has to be below 60 degrees in the sky. So latitude. Navigators would ideally determine their latitude by making a noon sight. What you do is you take your sextant and you, just before noon, begin to watch the sun. It'll slowly rise, reach a maximum value, stop, and then begin to fall back. That maximum altitude of the sun is a very quick and easy way of determining your latitude. The calculation that you need to get your latitude involves just addition and subtraction. There's no multiplication. It's a wonderful, quick and easy sight to be able to do. During the expedition, the Powell expedition that occurred in the summer months, the sun, however, is crossing that meridian at an altitude of above 60 degrees. So you can't do the classic noon sight. Instead, what Powell did was to use meridian transits of Saturn, which was well placed in the early evening sky for that purpose, and also meridian transits of stars, mostly Altar, but he also did one other. There is another way of determining your latitude. The north celestial pole is the point in the sky about which all other stars appear to rotate on a daily basis. The altitude of that celestial pole in the sky is equal to your latitude. The pole star Polaris is quite close to that point. It's not exactly at it, and in 1869 it was 1.4 degrees from the north celestial pole. So you have to apply some corrections. If you didn't apply corrections, your latitude that you determine could be off by plus or minus 84 nautical miles, which really isn't helping much. Now, the various journals and diaries of expedition members describe the locations where their campsites were, where Powell carried out his most extensive rounds of sites in quite a lot of detail. And so we can locate these on modern maps, and we can locate the latitude of them. And we can then compare those to Powell's observations. And we see that he was clearly a skilled observer. His average errors are typically below about half an arc minute, corresponding to an error on the ground of half a nautical mile, which is quite good. So here from the journal is a meridian altitude site of Saturn for latitude. And you see what he says here. Observation for latitude, July 19th, 1869, junction of the Grand and Green, meridian altitude double Saturn. And it's double because he's using his artificial horizon to make the measurement. And the double altitude that he measures is 62 degrees, 40 minutes, 20 seconds. He's also recorded here a very important quantity, which is the index error, and it's minus 1 arc minute in this case. And that's essentially the zeroing error of the sextant, and it needs to go in when you actually make the reduction. Here's a round of sites for determining latitude from the altitude of Polaris. This was made a day earlier from the same location. You see, he says he's measuring the polar star. And there are two columns here. The left-hand column is the double altitude of Polaris, and then the right-hand column is the watch time when the observation was made. And he's recorded the index error both at the start and the end of the round of sights. So that was latitude. Longitude, how do you find that? Well, longitude really is simply the difference between your mean time and Greenwich Mean Time. Every hour that your mean time is behind Greenwich Mean Time means that you're a further 15 degrees west of Greenwich in longitude. Now, marine navigators would, as part of their standard practice, take a time sight to determine local mean time. And that involves measuring the altitude of the sun where it's as close as possible to either due east or due west. And I probably pointed in the wrong direction. But at such times, of course, the sun tends to be rather low in the sky. So this is not something that you can do when you're sitting at the bottom of a canyon. So to determine local mean time, Powell used the method of equal altitudes of the sun, which I'll talk about in a little while. The second piece that you need for longitude, in addition to your local mean time, is Greenwich Mean Time. And the easiest way to get Greenwich Mean Time is simply to read it from the chronometer. But unfortunately, following the swamping of the Emma Dean, the boat, this wasn't an option for Powell. He did still have a working Elgin watch, but by looking at the observations that he made through the course of the expedition, it's possible to see that that was operating erratically. So, in an attempt to salvage the situation, Powell attempted to make observations of lunar distances, and that's a way of getting GMT from the position of the moon in the sky against the background stars. But all indications are that this is not something he'd really done and wasn't familiar with how to carry it out successfully. So, finding local mean time by equal altitudes of the sun. What you do is you note the time when the sun passes through some specified altitude in the morning, and then you note the time when it descends through that same altitude in the afternoon. Now, if the sun were fixed in the sky against the background stars, the time that it crossed the meridian, local apparent noon, would occur halfway between those two times, or the average of the two times. But the sun changes its declination during the day, and so you have to apply a correction for that. Moreover, once you have the time of local apparent noon, that's not the time that your watch would show, that's the time a sundial would show, and that can vary from standard time by up to 16 minutes. So there's an additional correction that needs to be applied there. That's actually quite easy to do. Once you have apparent time, you get local mean time by adding something called the equation of time. So here's a round of sights that Powell performed for the equal altitudes of the sun. You see its observations for time, equal altitude sun, 18th of July, again at the junction of Grand and Green. There are three columns here. This left-hand column is the double altitude of the sun. The middle column is the watch time when the sun was observed to pass through that altitude in the morning. And the right-hand column is the time when the sun was observed to descend through that altitude in the afternoon. Down here, he's averaged these. And the reason for doing that is to, any one of these observations is going to have a certain amount of random error in it. By averaging them, you hope to suppress random errors. What is interesting here is that he's not recording the index error as he does with all his other types of sights. And the reason is that for this equal altitude observations, you don't actually need the absolute value of the altitude through which the sun is passing. You just need to make sure that it's the same in the morning and the afternoon. So provided your index error doesn't change, you don't care. So here's the Powell calculating this correction that I mentioned for the fact that the sun's declination changes through the course of a day. And so we've replicated this calculation here on the right-hand side and labeled all the quantities. And although we disagree with, or don't quite agree with some of the smaller decimal places, in the intermediate calculation, the result that we get and that Powell gets agree to within half a second, which is just fine. So, as I said, all this is very fine to know what your local mean time is, but if you don't have Greenwich Mean Time, you've got nothing effectively. So Powell attempted to do lunar distance sights as a way of getting Greenwich Mean Time. Now the moon moves against background stars at a rate fast enough that you can effectively use it like the hands of a clock to basically read off GMT. The ideal way of performing this observation is to have 3 skilled observers simultaneously measure the altitude of the moon, the altitude of the sun, and by turning the sextant on the side, measure the lunar distance between the moon and a star. Now, it doesn't have to be a star, it could be the sun or it could be a planet, but for this example, we'll assume it's a star. You can also do this if you're by yourself, but you have to start by measuring the altitudes of the star and the moon. You then do a series of lunar distance measurements, and then you end with another measurement of the altitude of the star and of the moon. You need to do all this in under 10 minutes. Otherwise, you can't, the reduction calculation becomes much more complicated. So here's an observation that Powell performed, the lunar distance sight Alta with the star Altair on the 15th of August at Silver Creek. You see the first line here, L with a little star. The first column is the watch time. The next column on the right is the double altitude of the star Altair. And he's done that on the last line here at the bottom as well. The second line is the watch time and double altitude of the moon's lower limb. And that appears again, the second last line. And we know it's the moon's lower limb because he's drawn this little line under the symbol of the moon to indicate lower limb. He's also recorded the index errors at the start and finish of his round of lunar distance sights. And these are lunar distance sights between the star Altair and the moon's far limb. And we know it's the far limb because of the little line that he's drawn on the far side of the moon's disk from the star. So this was Powell's attempt to obtain GMT. As I said, he'd probably not practiced this very often, if at all. We find that, in fact, some of his early rounds of sights last for over an hour, which is certainly very non-standard. There is no indication, and it seems unlikely that he would have planned to do any sort of reduction of these observations during the course of the expedition, and so would have had no feedback on how he was doing. And when we look at them in detail, we find that all of the lunar distance sights that he makes show some sort of inconsistencies or errors and are not actually usable for finding a longitude in practice. And so the discovery of longitude of these places along the Colorado River had to await subsequent expeditions. Thank you.